Voyager 1 has NASA buzzing with excitement, and a bit of worry. The team had simply instructed the aging spacecraft to switch on its heater. But what happened next caught everyone completely off guard and even sparked fears that communication with the probe might be lost forever. Curious to find out what unexpected issue emerged in the vast emptiness of interstellar space, and how a decades-old backup system helped Voyager 1 send a signal back to Earth. Stick around to uncover the full story of how this legendary space traveler managed to reach out from nearly 25 billion kilometers away. Turning on the heat seems like a straightforward task, at least here on Earth. But things get a lot more complicated when you're trying to warm up a spacecraft that's been journeying through space since September 5, 1977. And now that Voyager 1 has crossed into interstellar space, keeping it operational is a challenge unlike any other for NASA's engineers. After all, the aging probe has been increasingly making headlines due to technical glitches that continue to challenge the engineers responsible for it. What was meant to be a routine command ended up turning into another problematic episode for Voyager 1 just a few months ago. So, what exactly happened? On October 16, 2024, NASA instructed the spacecraft to activate one of its heaters. However, less than 2 days later, troubling news emerged. The Deep Space Network could no longer pick up Voyager 1's signal. The delay in discovering this issue, once again, came down to the vast distance separating the probe from Earth. A message sent to Voyager 1 takes about 23 hours to travel the vast distance of nearly 25 billion kilometers, and just as long for any reply to make its way back to Earth, assuming it returns at all. To understand why this wasn't the case recently, it's important to remember that Voyager 1 is equipped with an onboard fault protection system designed to automatically handle issues. For example, if the spacecraft's power system becomes overloaded, this system will shut down non-essential components to conserve energy. In this instance, however, the heating command unexpectedly activated the fault protection system, even though Voyager 1 had sufficient power to carry out the command. This added to the confusion surrounding the incident. To better understand the situation, it's important to briefly mention that the probe typically communicates with Earth using what's known as an X-band radio transmitter. This transmitter operates at a frequency range between 8 and 12 GHz, allowing it to send data from interstellar space to Earth at relatively high speeds. However, after contact with the probe was lost, experts correctly suspected that its error protection system had automatically reduced the data transmission rate. From an energy-saving standpoint, this made sense, as the lower mode consumes significantly less power. Unfortunately, and this is the key issue, switching to this low-power mode also alters the characteristics of the X-band signal, making it more difficult for NASA's Deep Space Network to detect and track. To everyone's relief, on October 18, NASA engineers successfully located the altered signal. However, this did not mean that the technical problems were fully resolved. Voyager 1 managed to phone home using a backup transmitter that hadn't been used in over 40 years. Although the probe initially appeared to be in stable condition, another issue quickly followed. Communication completely broke down the next day. Engineers believed the fault protection system was once again to blame. It likely misfired and incorrectly shut off the primary X-band transmitter, switching the signal over to the older S-band instead. What surprised everyone was that the S-band transmitter actually worked. It hadn't been used to communicate with Earth since 1981. While the S-band does consume less power than the X-band, it also operates at a lower frequency, which means it transmits less data and takes longer to do so. That's precisely why it was only intended as a backup system. Mission planners knew from the start that cosmic radiation could damage onboard electronics, and they designed the spacecraft with that risk in mind. Given the incredible distance Voyager 1 has traveled, the fact that it was able to resume communication at all is a testament to the foresight and engineering behind the mission. At first, there was uncertainty about whether the span signal could be detected at all, or if Voyager 1 had been lost for good. Fortunately, the signal was eventually found. But that led to a critical decision. What should be done next? Given Voyager's history with error protection systems, simply reactivating the X-band transmitter was considered too risky. This kind of step should only be taken once the root cause of the system issue is fully understood. However, based on past experience, such error analysis can take weeks, sometimes even months. Did that mean the team would have to give up on contacting Voyager 1 in the meantime? Thankfully, no. As mentioned earlier, the span transmitter was still available. So, on October 22, NASA sent a command to test if it was still functioning properly. And just 2 days later, a response came through. A stable connection had been re-established. In a remarkable twist, NASA's backup transmitter, unused for more than 40 years, turned out to be the key to saving the mission and keeping contact with humanity's most distant spacecraft. But that raises the question, what's the current status? Is Voyager 1 still transmitting through its emergency system? No, according to NASA, everything is now functioning normally. In a press release dated November 26, 2024, NASA confirmed that the radio communication issues had been successfully resolved. Voyager 1 is once again using its primary X-band transmitter. This is just one example of how the life of the Voyager probes is being extended, despite their age. But the reality is that nearly 5 decades in space have taken a toll on these twin spacecraft. We have to gradually accept that even the most remarkable success story in space exploration will eventually come to an end. When Voyager 1 and Voyager 2 launched in 1977, no one could have predicted they would become the longest operating spacecraft in history. Originally designed to explore the outer planets, then still shrouded in mystery, the mission was only expected to last about 5 years. Yet here we are today, still receiving data from these extraordinary explorers. We now know that the spacecraft have surpassed their originally expected lifespan by nearly tenfold and have traveled farther into space than any other human-made object. This naturally leads to a crucial question: how is this even possible? Put simply, how can probes built with 1970s technology still be cruising through space without interruption, continuing to send us valuable data from interstellar space? Keep in mind, the onboard computers of the Voyager probes have less than a millionth of the storage capacity of a modern smartphone. Their transmission speeds are about 38,000 times slower than a typical mobile phone connection, and the scientific data they gather is still recorded on magnetic tapes. While the Voyager probes are undeniably feats of durable engineering, the plutonium in their thermoelectric power sources now produces only about half of the power they had when launched. To keep these aging space explorers powered up, NASA has been strictly managing their energy consumption for quite some time. Years ago, all non-essential systems were turned off, followed by the shutdown of a backup system in 2023 and the plasma sensor on Voyager 2 in 2024. Despite these efforts, the power supply continues to decline, losing about 4 watts annually, forcing NASA to make additional cuts to keep the twin probes operational. Most recently, on February 25, the cosmic ray subsystem on Voyager 1 was turned off. This subsystem, made up of 3 telescopes, measures the energy and flux of high-energy protons from both the Milky Way and the Sun. It was this data that confirmed in 2012 that Voyager 1 had crossed beyond our solar system's boundary. Then, on March 24, Voyager 2's sensor for charged low-energy particles was also powered down. This sensor mainly detects the lower energy particles found in cosmic radiation, as well as those from the solar and galactic magnetospheres. Consequently, the veteran Voyager probes now operate with only 3 of their original 10 instruments. On Voyager 1, these are the magnetometer, the plasma wave subsystem, and the low-energy charged particle sensor, though the latter is planned to be turned off in 2026. Voyager 2 still carries the magnetic field sensor, the plasma wave instrument, and the cosmic radiation subsystem, but that last one is expected to be retired in 2 years as well.